Bismillahirrahmanirrahim. Assalamu alaikum. My name is SHAH and my group member name is SAFFARAD. Today we are going to give a presentation about the topic of linear programming simplest method, theory and application. First of all, I will tell about you about the simplest method. What is simplest method? Standardized techniques in linear programming for solving an optimization problem. Typically, Bismillahirrahmanirrahim. Assalamu alaikum. My name is SHAH and my group member name is SAFFARAD. Today we are going to give a presentation about the topic of linear programming simplest method, theory and application. First of all, I will tell about you about the simplest method. What is simplest method? Standardized techniques in linear programming for solving an optimization problem. Typically one involving a function and several constraints expressed as inequalities. The inequalities define a polynomial region and the solution is typical at one of the vertices. The simplest method is a systematic procedure for testing the vertices as possible solution. Objective function. The solution of linear programming problem reduces to finding the optimum value, largest or smallest, depending upon the problem of the linear expression. It is called objective function. For example, we have f is equal to s1, x1 plus so on. Subject to a set of constant expressed as inequalities. For example, we have a situation of a11, x11 plus so on greater than or equal to b1 or less than equal to b1 maybe. Now there are 8 steps involving in the simplex method. The first one, express the problem in equation form. Second one, write the inequalities in the form of equalities. Third one, determine an initial feasible solution. Fourth, write initial table. Fifth, determine the criteria for optimality. The sixth one, select an entering variable using the optimality condition. Seventh one, select the leaving variable using the feasibility condition. And the eighth one and the last one, write the optimal solution. Now we are discussing in one by one in detail. First one, express the problem in the equation form. And we have maybe in the statement form, so we have to convert it into the equation form. In this case, the given problem is in the form of statement. We need to translate it in equation. And the second one, write the inequalities in the form of equalities. In this step, we have generally three types of equations. The first equation may be less than and equal form. For example, we have example 4x1 plus 3x2 less than equal to 240. Whenever we have a less than and equal to situation, we introduce a slack variable to solve this kind of problems. And note that slack variables are always added. So our new equation will become 4x1 plus 3x2 plus s1 is equal to 240. S1 is the slack variable. Now we have another type which is equal form. For example, we have equation 4x1 plus 3x2 is equal to 240. As we have a equal form, now we introduce a artificial variable. Introduce artificial variable to solve this kind of problem. Note that artificial variables are always added, and our new equation will become 4x1 plus 3x2 plus a1 is equal to 240. A1 is the artificial variable. Now we have another form, and the third one, which is greater than and equal to form. For example, 4x1 plus 3x2 greater than equal to 240. Whenever we have a equal to and greater than form, we introduce a surplus variable, and surplus variable are always subtracted, and our new equation will become 4x1 plus 3x2 minus s1. Now note that whenever we have surplus variable, we always introduces our artificial variable to solve this kind of problems, and artificial variable are always added. So our new equation will become 4x1 plus 3x2 minus s1 plus a1. S1 is minus s1 is surplus variable, and the plus a1 is artificial variable. It is only for the maximization problem. Now we have the third step, determine an initial feasible solution. To determine an initial feasible solution, see how much equation and variables are there. This will help in deciding how much variable will be given arbitrary values. We have formula of arbitrary values. Arbitrary values is equal to number of the variables minus the number of the equations. So for example, we have 6 variables and 4 equations. So arbitrary values become 6 minus 4 is equal to 2. So the two variables will be the given arbitrary values equal to 0. Note that all the variables and the right hand side of the equation will be non-negative. Now the fourth one step, write initial table. So whenever we have a table, we have two types of variable. One basic variable, one is basic variable, and the other one is non-basic variable. Basic variable, all the non-zero variables from the initial solution, and non-basic variables having zero values called non-basic variables. And we have the right hand side. The right hand side of every equation will come here. The coefficient of constant will be written here, and the coefficient of the objective of function is written here. Now the fifth step, determine the criteria for optimality. Solution of the current table is said to be optimal if all the objective function coefficient become non-negative positive. Note that whenever we have a negative values, the solution is not optimal. We required all the positive values. Now the sixth step, select an entering variable using the optimal condition. The interim variable in the maximization problem is non-basic variable with the most negative coefficient in the F row. The optimum is reached at the iteration where all the F row coefficients are non-negative. Now this seventh step. Select a leaving variable using the feasibility condition. In case of maximization, the leaving variable is the basic variable associated with the smallest non-negative ratio with a strictly positive denominator. There is no need to take ratios for negative and 0 because they cannot be entered into the basic variable. Now the eighth one and the last. Write the optimal solution. When the solution criteria is satisfied, the value of the decision variable will be taken from the table from the corresponding right hand side. Note that we put these values in the original maximization function to calculate optimal point. Now this is the end of my presentation. From onward, SAFFARAD ASHFAQ will be presenting you on this topic. Thank you so much. Allah Hafiz.
Assalamu alaikum. My name is SAFFARAD ASHFAQ. I'm going to illustrate the problem through simplex method of linear programming. So here I start the illustration as we have given the objective function, which is f is equal to 5x1 plus 4x2. So we have to maximize the profit through simplex method of linear programming. Now again, this objective function has subjected to different constraints, and these constraints are 6x1 plus 4x2 less than or equal to 24. We name this equation as equation number 1. x1 plus 2x2 less than or equal to 6. We name this equation as equation number 2. Minus x1 plus x2 less than or equal to 1. We name this equation as equation number 3. x2 less than or equal to 2. We name this equation as equation number 4. So x1 and x2 are the two variables we used in these constraints. So x1 and x2 greater than or equal to 0. It means that these are the non-negative constraints. So we move to the step 1 of the simplex method of linear programming, which is rewriting constraints equations into the homogeneous order. As we move back to the previous slides, we can see that the equation number 4 contains only one variable, which is x2. It means that the equation number 4 is not in an homogeneous order. So we have to make this equation into an homogeneous order. To make this equation into homogeneous, we have to add another variable. So we are adding 0x1 to this equation to make this homogeneous. By adding 0x1, all of our equations are now in homogeneous order. So we have to move to the next step, which is step number 2. Step number 2 is inequalities constraints in equation form. So we have to write inequalities in equation form by adding slack variables. We are choosing slack variables in this case because these equations are less than or greater to. So as we can see that an example in this slide, 6x1 plus 4x2 plus s is equal to 24. S in this equation is a slack variable. Let s1, s2, s3 and s4 be the slack variable for first, second, third and fourth constraint respectively. So our constraints would be 6x1 plus 4x2 plus s1 equal to 24, x1 plus 2x2 plus s2 equal to 6, minus x1 plus x2 plus s3 equal to 1, 0x1 plus x2 plus 4 equal to 2. We name all of these equations as 5, 6, 7 and add respectively. As we rewrite the objective functions, f minus 5x1 minus 4x2 is equal to 0. We move 5x1 plus 4x2 to the left hand side of the equation to make the right hand side of the equation as a constant value. So x1, x2, s1, s2, s3, s4, these are the 6 variables we used in our constraints. So x1, x2, s1, s2, s3, s4 greater than or equal to 0. So we move to the step 3 of the simplex method of linear programming, which is initial feasible solution. So we have to calculate arbitrary values of these constraints. Arbitrary values consist of number of variables minus number of equations. We are choosing total number of variables 6, which is x1, x2, s1, s2, s3, s4, and number of equations, which is 4. So 6 minus 4 is equal to 2. It means that we have to put 2 variables is equal to 0 and we have to put x1 equal to 0 and x2 is equal to 0. Putting above values in objective function f is equal to 5x1 plus 4x2 and equation 5 to add. So by putting the x1 equal to 0, x2 is equal to 0, we will f is equal to 0, s1 is equal to 24, s3 equal to 1, s2 is equal to 6, s4 is equal to 2. Now we move to the step 4, which is initial tabulation. We have to make an initial table for the coefficient of each variables. The initial table consists of basic variables, and basic variables are s1, s2, s3, s4 and objective function f. And the upper side of the table consists of non-basic variable, which includes x1, x2, s1, s2, s3, s4 and a column of right hand sides of each equation and column for ratio as well. We have to fill this table by the coefficient of each variables. After filling this table, we move to the step 5, which is checking the criteria of optimality. For finding optimal solution, we have to check the coefficient of objective function. If the coefficient of objective function is positive, then that will be an optimal solution. If the coefficient of objective function is negative, then that would not be an optimal solution. In this case, the coefficient of objective function is negative, so we have to find the minimum coefficient of objective function, which is minus 5. So the corresponding column would be our pivot column. So then we have to find the ratio. So how to find the ratios? We have to divide the right hand side's values to the corresponding pivot column value. So 24 divided by 6 is equal to 4, and ratios can be 5, so on as well. Then we have to find the pivot row as well. The minimum value a ratio column consists would be an pivot row. So the S1 row contains the minimum value, which is 4. So S1 will be an pivot row. Then next we have to find the pivot number. The intersection point of pivot row and pivot column, the point where both of the lines intersects, the number in that point would be an pivot number. And we move to the step 6. Step 6 is that in which we select entering variables. The lines pivot row and pivot column will intersect and at the non-basic variables, and x1 would be our living variables, and at step 7 we have to find the living variables, and s1 would be our living variables. So these two steps are very important for making the new table. We have to know that our entering variable and living variable, because in the next table living variable can be replaced by an entering variable. So now we have to do that some other tasks. We have to check some cross-checking measures. For cross-checking measure is that the basic variables are equal to 1 under the respective columns, and all the other values in columns will be 0. So if you don't have 0 or 1 on this position, it means you have done something wrong. So now we have to do calculation for new iteration. New pivot row is equal to 1 divided by pivot number multiplied by old pivot row. We are going to use this formula to find new pivot row. 1 divided by 6 multiplied by old pivot row. By calculating these values, we got new pivot row, which is 1, 2 by 3, 1 by 6, 0, 0, 0, 4. Now we have to find new rows. New row is equal to old row minus pivot column coefficient multiplied by new row pivot. Then first we have to find new S2 row is equal to old row minus coefficient of pivot number minus coefficient of pivot column multiplied by new pivot row. So after calculating, we got new S3 row, which is 0, 4 by 3 minus 1 by 6, 1, 0, 0, 2. Now new S3 row is equal to old row minus coefficient of pivot column multiplied by new pivot row. After calculating, we get new S3 row 0, 5 by 3, 1 by 6, 0, 1, 0, 5. Now new S4 row is equal to old row minus coefficient of pivot column multiplied by new pivot row. After calculating these values, we got new S4 row is equal to 0, 1, 0, 0, 1, 2. Now new F row is equal to old row minus coefficient of pivot column multiplied by new pivot row. We got the new F row, which is 0 minus 2 by 3, 5 by 6, 0, 0, 0, 20. Now we have to replace all the rows in the new table with the corresponding rows. Now again replace the new rows with the corresponding rows. We again make a new table and do the same procedures and check the criteria of optimality. Now this is not an optimal solution because coefficient of objective functions has contained the negative value. So we have to do again the same procedures. We have to find the new pivot row and new rows as well. New pivot row is equal to 1 divided by pivot number multiplied by old pivot row. We have to find the values. So after calculating these values, we got new pivot row 0, 1, minus 1 by 8, 3 by 4, 0, 0, 3 by 2. Now new row is equal to old row minus pivot coefficient column multiplied by new pivot row. New S1 row is equal to old row minus pivot coefficient column multiplied by new pivot row. After calculating these values, we get new S1 row is equal to 1, 0, 1 by 4 minus 1 by 2, 0, 0, 3. New S3 row, old row minus coefficient of pivot column multiply by new pivot row. After calculating these values, we get new S3 row, which is 0, 0, 3 by 8, minus 5 by 8, 1, 0, 5 by 2. New S4 row is equal to old row minus coefficient of pivot column multiplied by new pivot row. After calculating, we get new S4 row, which is 0, 0, 1 by 8, minus 3 by 4, 0, 1, 1 by 2. New F row, old row minus coefficient of pivot column multiplied by new pivot row. After calculating, we get new F row, which is 0, 0, 3 by 4, 1 by 2, 0, 0, 21. So again, put all the new rows into the corresponding rows in the next table. So the table is look like that. Again, for formulating a table, we have to put all of the new rows in this table, and then again we have to check the criteria of optimality, whether this is an optimal solution or not. Check the coefficients of objective functions, and in this case the coefficient of objective function is positive, and now this is our optimal solution. So now we move to the step 8. We have to calculate whether the coefficient, whether the right hand side of the objective function is equal or not. We have to put the right hand side of x1, which is 3, and x2, which is 3 by 2, putting these values in objective function, and objective function is f is equal to 5x1 plus 4x2. F is equal to 5x1, put the value of x1, which is 3, plus 4, put the value of x2, 3 by 2. F is equal, by calculating 4, 3 by 2 plus 5 into 3, we get f is equal to 15 plus 6, f is equal to 22, which is the maximum value of f. The solution is, the condition of optimality is satisfied. And that's end of our presentation. Thanks for listening as well.